Previously, we talked about how to calculate the area between functions of x. In this video, we're going to look at what happens if they're different, if they're other kinds of functions, so not functions of x. And first of all, we're going to look at functions of y. So for example, in this case, you can see that these are functions defined with respect to y. So that would be like y equals, sorry, it wouldn't be y equals, it'd be like x equals y cubed plus 2y. That's a function of y. So this is the same as x, but instead of the upper and lower functions, use farther to the right minus farther to the left. And this is because if we integrate the u of y, we're going to get this whole area right here. Same as with x, it's just the area between the function and the y-axis. And then if we integrate v, we're going to get this area right here. And so subtracting the two leaves us that blue area. Whoops, so I want to write down the equation here. So in this case, the area would be the integral from c to d, because we want to start with the smaller y value and go to the larger y value, just like when we integrate with x. And it would be, in this case, u of y dy minus the integral from c to d of v of y dy. In other words, you could also write area is equal to c to d of u of y minus v of y dy. So let's look at an example for this. So find the area between these curves and the x-axis. So if we want to integrate with respect to y, that means we're going to need to define these in terms of y. So f of x equals x squared implies that we can write a function f of y is equal to the square root of y. And that's just because we have y equals x squared, which we can rewrite as x equals square root of y. Technically, it should be plus or minus in both of these cases, but if we look at our graph, we're only taking the positive part. So we're just going to have the plus. Like so. And then the other function, g of x is equal to 2 minus x. So y is equal to 2 minus x. So that implies that x is equal to 2 minus y, right? Yep, 2 minus y. So now we've got these two functions of y. So we're going to integrate, and we're going to integrate our y values. Our y values go from 0 here up until the intersection at 1. So from 0 to 1. And you can double check that by plugging in things here. If I plug in x, if I set these equal to each other, square root of y is equal to 2 minus y. You end up finding that the intersection is 1. Because you can square both sides, and that will give you 4 minus 4y plus y squared is equal to y, and then continue to solve that through, and you'll get 1 and the other negative value over here, but the 1 is the one that we care about. Okay, coming back here, integrating from 0 to 1, and we're going to take the upper or the outer function, the one that's farther away from the y-axis. And this is the g of x, so it's going to be our g of y. So we're going to take 2 minus y minus, and then square root of y dy, and that will be equal to, when we actually integrate it, 2y minus 1/2 y squared minus 2/3 y to the 3/2, integrated from 0 to 1, and if you keep simplifying that down, you'll get 5/6, like so. This can be done with x values, and I'll set that up for us really briefly here, just so that you can see it and be familiar with it. But it would be something like this. So if we do it with y, x would be the integral from 0 to 1 of x squared minus 0 dx, because we're integrating essentially this minus the 0 value, plus the integral from 1 to 2. Sorry, that should be a 2 there, not, oh no, that should be 1, because it was y values, not x values. And then from 1 to 2 on the x values of 2 minus x minus 0 dx. So you can always use either method, either integrating with respect or integrating with respect to y. It's just what your preference is, and some will be significantly easier. For example, this first one, for this example, the y, we can do this all in a single integral. X, we have to split it up into 2. But it's just what ends up being easier. And as you practice, you'll develop that intuition of which you want to do for which. Next, we're going to look at polar coordinates. So when you integrate with polar coordinates, it finds the area between the curve and the origin. And so this you can think about as like pizza slices. So if I integrate from one angle to another angle, so this is theta 1, this is theta 2. If I integrate that, I'm finding this area in between, all the way out until the function where that is r of theta. So notice it's not, to the origin or to the axes. It's along these, following these angle rays going outwards, and it's between those. Likewise, if I went from, say, this angle to this angle, and my function was, something like that, I'd calculate this area here. So we're always going to have these kind of straight edge pizza slices or pie slices. If I went from 0 to pi over 2, then it would be, something like this, because we're actually going from this angle to this vertical angle, the horizontal axis to the vertical. If you want to integrate and find that area, and f is some function of theta, the area kind of contained by it is going to be 1/2, and if it's the interval alpha is less than or equal to theta is less than or equal to beta, just because with angular quantities we tend to use the Greek alphabet in math here, just to make sure that it's kind of easier at a glance to know that it should be polar. Keep drawing my betas poorly. But that should be from alpha to beta of f of theta squared d theta. Or in other words, 1/2, or you more commonly see it, alpha to beta of r of theta squared d theta. So this is the expression to find the area. Notice it's not just integrating the function. We have to use this special form. We need the 1/2 and we need to square the function, square r. This is because of, like, basically if you do Riemann sums to figure out this area, it ends up giving you an extra factor of r and giving you this 1/2. The derivation of this is not terribly important, so I'm going to skip it for now. But if you want to know how to do it, you can look it up online or ask me about it and I'll show it to you. But if you just care about, passing the class or being able to work with it, you can just memorize this formula. So really quickly, I'm going to do an example. Find the area between the curves here. You'll see that we've got r equals 6 sine theta and r equals 2 plus 2 sine theta. So we're going to integrate from one interval, so from alpha to beta, and now we need to take the outer function, the one that's farther from the origin, so we're going to take 6 sine theta minus the inner function, and these need to get squared, minus the inner function of 2 plus 2 sine theta squared, the 1/2, because remember it's 1/2 r squared, 1/2 r squared minus 1/2 the other r squared, but because we can combine similar integrals, we end up with our setup like this. To find these points right here, I'm just looking for intersections of the curves, so I can set them equal to each other. So 6 sine theta is equal to 2 plus 2 sine theta. That ends up giving me, if I rearrange this a little bit, sine theta is equal to 2/4, which is 1/2. And that means that we're going to get theta equals to pi over 6 and 5 pi over 6, because those are the first two places that sine of pi over 6 will be 1/2, sine of 5 pi over 6 will be 1/2. And that kind of makes sense when you look at your graph here. That's about 1/6 of the way around, and this is about 5/6 of the way around. So that's what we have here. So that means we can rewrite this as 1/2 integral from pi over 6 to 5 pi over 6, and then all the rest of the stuff, d theta. Expanding this out, we end up with, I'm going to skip a couple steps here, but we end up simplifying to the integral from pi over 6 to 5 pi over 6, 36 sine squared theta minus 4 plus 8, 4 sine squared theta, d theta. These sines squared, you can use, there's just a, what's the word I'm looking for? There's an identity, a trig identity that lets you replace this with 1 minus cosine 2 theta over 2, and that'll end up being easier to integrate. So we'd replace both of those, and then at that point it's just some u substitution and other stuff that I'll leave you to practice. If you get stuck or want me to help you with it, let me know. But for sake of keeping this video on the shorter side, I'll leave the rest for you, and ultimately you end up getting area is 4 pi. But again, this right here, you don't have to memorize this. It's just, I happened to pick a problem that involved using a trig identity. If you ever get, squared sines or sines of 2 pi's or 2 thetas, things like that, look up to see if there's an identity that you think will help, and then just give that a shot. But that's the idea behind finding areas of polar curves.